Welcome everyone to this session. Today we are gonna discuss something called neighborhood. If you are aware about the terminology used by Robert G. Bartle in his textbook in Introduction to Real Analysis, epsilon neighborhood or delta neighborhood, similar kind of idea we are gonna capture here. I'm not going into that thing. I left it for you guys to explore what do you mean by epsilon neighborhood or delta neighborhood around a point. Of course, that thing would be, indirectly we will be covering that thing in examples. So, let me start with this, very important concept in topology. You will see as far as we will go that you cannot avoid this thing at all. So let me begin with the definition. So let X tau be a topological space. And X belongs to capital X. We say capital N sitting inside X. We say capital N sitting inside X is a neighborhood. Of X in, of course, my topological space X tau. Topology is gonna matter here. So, okay, if there exists an open set U in X such that what should happen? X should be inside this open set U and this U should be inside capital N. So if we have such a set N for which we have an open set which contains the point and that open set is sitting inside the set N, then what we are gonna call N is a neighborhood of X. Let me have few remarks about this definition. Number one, rather than spelling the whole word neighborhood, neighborhood, I have spelled it because otherwise I may do a spelling mistake in this word. We will just write nbd, but we are gonna pronounce it neighborhood only. So it's a kind of short form or abbreviation for the word neighborhood. This is very common thing in topology. Another thing, a layman may think neighborhood for an object. What I mean is like a house or a country. So what a is our usual thinking about neighborhood? The things nearby, right, is the collection of objects nearby, right? But this is not true in topology. Can you tell me why? You may stop the video and think about it. Now let me give you reason why. Because for any x in x, okay, what is x? X tau is a topological space. I'm continuing remarks on that definition, so I'm assuming I have a topological space and these things are happening. So for any x in x, note that x belongs to x, of course, which is inside x, and x is open in x. No? Right? So what is this? What you can imply? From the definition of neighborhood you can imply, this implies x is a neighborhood of small x. So you see, your space can be uncountable or, right, very large, or even like R is also, real numbers is also very large, and if you give any topology there, then any point you take, R is neighborhood of that by the definition. So the usual, the intuition of neighborhood, of course that intuition inspires this definition, but that intuition is not, mathematically accurate when it comes to topology, neighborhoods or neighborhoods in topology. So let me give you one more remark, or maybe two more. I want you to verify this thing. Every open set is a neighborhood of each of its points. Please verify it. This is easy to check, something like above what we have written in purple color. The same kind of logic will hold here. Now, a final remark I want to give. As far as we go deep in this topic, we will learn something called local and global properties. Rather than, since I'm talking about topology, let me use the word, or maybe just this. This is fine. Local, global properties. Let me correct the spelling of global. Global properties in topology. So we will learn about it. Right now I am just writing this as a remark so that, when we are gonna discuss those things, you can link the two things. The concept of Neighborhoods provide a link between above two. What above two? The properties, local and global properties. We will be defining some concepts globally and locally. You will see this convention or definition of neighborhood is gonna help us there. So let me move on further and discuss few properties about neighborhoods. So let us have it as a proposition. Proposition. Let me call this proposition as star because I'm gonna use it. So let X tau be a topological space. And for each X in X define, we are gonna define a collection. We will denote it by this stylish n. I mean something you can use the command in LaTeX, math cal. Okay, n. If you use that, you will got the symbol accurately. Okay, I will just twist somewhat this capital N and write it as stylish. So what is this thing is collection of n in X such that n is a neighborhood of small x. So one thing, since this we are defining a collection, you should always check, is this collection non-empty? So what is your answer? It is, right? Because the whole space is always there. Okay, good. Then number one, which is sort of obvious. X belongs to capital N for every n in stylish nx. Right? Number two, if n comma m belongs to nx, in other words, if they are neighborhood of point x, then n intersection m is also a neighborhood of x. Good. Let us proceed. If n is a neighborhood of x, and capital M sitting inside x such that n is also sitting inside capital M, and this is in x, then what my claim is, this M is also a neighborhood of x. So it is in stylish. Okay? Now, fourth thing. For any net nx, let us define a set. Define n circle. How we are defining it? Basically, this is collection of all points in n such that n is a neighborhood of that point. So n belongs to stylish n suffix y. So what our claim is, this n circle is also a member of n suffix x. It is also a neighborhood of the point x. If you are not clear with the set n circle, let me give you an example. Example n circle. So let us see. So consider real line R. I have already told you what is real line R, so you know what topology is there. I'm not gonna repeat it now. So if you consider real line R, and let's have a set, okay? Say capital N is equals to closed at 2, open at 3, okay? Now, clearly, if you take 5 by 2, I think it's sort of midpoint, right? 3 plus 2 by 2 belongs to open interval 2 to 3, which is contained in N. Note that 2 to 3 is open in R, right? Real line R. You know it. This is from, metric spaces. Or if you don't know, you can try to prove it, that this set is an open set. Basically, this is a member of topology induced by the usual metric on R. Okay, usual metric means Euclidean. So I have repeated sort of what is real line. Okay, so what it implies, guys? N is a neighborhood of 5 by 2. That is, N belongs to N suffix 5 by 2. Very nice. Let us see what is N circle. So note that for any point, for any y in this open interval, which open interval? 2 to 3. What you have? Y belongs to, of course, this open interval, which is sitting inside capital N, and this is open in R. So by same logic, what you have? N actually belongs to N suffix y for every y in this open interval, right? So what you have? So this implies open interval 2 to 3 is contained in N circle. Why, guys? Because N circle is precisely the collection of points for which N is in N, for which N is a neighborhood of those points. Now, also note that two does not belongs to N circle. Why, guys? I left you this as an exercise. Why? You may have intuition of it, but you should write properly. Like you remember in some previous lecture we have shown examples of open and closed set. We have written properly even if we have intuition, because intuition can be sometimes wrong. I am gonna give you an example when we will be doing something called quotient spaces. So let me write the final conclusion. This implies N circle is what? Open interval 2 to 3, because it is we have analyzed all points in N for which N is neighborhood of that given point, right? So it is neighborhood of all these points in open interval 2 to 3, but not 2. Good. So this was an example, like to make you guys comfortable with, you see, these notations what I have written in green color. So remember these statements for some time during this lecture. If you don't, you can always stop the video and continue later on. So let me prove it. All of these. Proof of star. The proposition I have denoted by star. Number 1. Clearly, if n belongs to nx, this means n is a neighborhood of small x. So this implies x is in n. This is by definition. Why? Because there will be an open set sitting inside n which contains that point x. So n is in n. So the usual, if we talk about my neighboring states or my right, so of course I include myself in that. Otherwise, there is, or my state. Otherwise, there is no point of the convention of or the otherwise we will just totally ignore the meaning of the terminology neighborhood. Okay, good. The second thing. So let n1, n2 belongs to n suffix x. What we have to show, guys, if you remember, we have to show that the intersection is also there. So what we are gonna do is, first of all, we are gonna apply the definitions of this. So n1 and n2 are neighborhood of x. It means there exist open sets u1 and u2 such that, I'm just writing the definition of neighborhood of point x, such that x belongs to n1, sorry, what I should write here, x belongs to u1 which is sitting inside n1, or let me write, like this, I, for I equal to 1, 2, right? Because n2 is also neighborhood. I have just written in a compact way to avoid, little bit of extra work. Now, what it means, guys, this implies x. X is in both of the ui's. So it means it is an intersection. Where was u1? Inside n1. Where is u2? Inside n2. So this means this should be sitting inside n1 intersection n2. Of course it would be in union, that's not a problem. Intersection n2. Now, u1 intersection u2. What can you say about this? This is open, right? Because finite intersection of open set is open. So what this concludes? n1 intersection n2 is a neighborhood of the point x. Good. Let us show the third one. You have what you have. So let n belongs to nx and m contained in x such that n is also sitting inside m. What you have to show, guys? You have to show m is inside nx. I request you guys to stop the video and try it, although I'm gonna do it. So let me argue it. So n in nx implies there exists u open in x such that x belongs to u, which is inside n. N is inside m. So just consider these things. This and finally this containment. So what you have, guys, if you consider this, I hope you get it, that m is a neighborhood of x. So m belongs to nx. See, these are, you may think this is very easy, but we are gonna do something with this, and that something is very important. So let me continue further for the fourth one. So what was n circle? N circle was all such y in n such that n is neighborhood of y. Okay. What we have to show? To show n circle is itself inside what? N circle is inside nx. Right? That is what we have to show. Again, let's use the definition. So what is n? N belongs to nx, right? So I should have written it. Since n is in nx, what it means, guys, this implies there exists open set u such that x belongs to u, which is further inside n. Very good. Let us observe something. So claim u is actually inside n circle. Can you tell me why? Because for every, say, alpha in u, we have alpha is in u, which is inside n. What is u? U is an open subset of x. So what it means, guys, this implies n actually belongs to n suffix alpha, right? So this implies alpha should be inside n circle. So where it was initially? In u. Now where it is? In n circle. So you see, you are done. But this implies u belongs to n circle. Now see, I hope you got it. We are done. If you haven't, let me write it. So x is in u, which is in n circle. U is open in x. So by definition, what this would imply? Definition of neighborhood. N circle is also a neighborhood of x. So you see, like this, we have proven these four things. This n circle is a very beautiful set. So now, let me have the main theorem of this lecture. Or let me, So let me name it in my own way. Topology constructed from neighborhood like sets. So we are gonna see a way to give a topology on some particular set X by something similar to neighborhoods. So let me write the statement, then you will be clear with this thing. What I have written here is neighborhood like set. Let me write it in small letters. So let me have theorem. This theorem is, let me tell you, very important. And I'm just gonna mention an application. Okay, I will not discuss that because that will, that would be a huge digression. So I don't want to do that. First, I want to develop, a strong foundation for topological spaces. Then we will be discussing those things maybe later on. Okay. So theorem. Let X be a set. For each x in X, assume there exists n suffix x. So stylish n I want to write. Note that this n suffix x and the above n suffix x are different things. above it was collection of all neighborhoods of X. But you see, I have started with a set, not a topology. So you cannot say it is collection of neighborhoods here. Okay. So assume there exists n suffix x contained in 2 to the power x for each x, such that n suffix x is non-empty and n suffix x satisfies 1, 2, 3 mentioned in star, the proposition above. So you see, those were just some properties. So those properties I want these n suffix x, these collections to satisfy. This is just collection of subsets of x which satisfies these three properties. Then what is our claim? If you define the collection tau to be like this, all such u in x such that what you should have, if x belongs to u, then we must have what? That u belongs to n suffix x. N suffix x is just a collection of some subsets. So what it is saying, it is collection of all sets in X. If you take any point in that set, then that set should be in the corresponding n suffix, that point. Okay. So what is the claim? Is a topology on X. Okay, so like I said to you, something like, these nx satisfies the properties which in some topological space neighborhood satisfies, right? So that's why I said neighborhood like sets. So it is topology, constructed from this way, and this is very important. Moreover, I want to mention one thing more. Moreover, if nx satisfies 4 also for every x in X, then nx is precisely collection of all neighborhoods of X in, or maybe we can use the better word, with respect to tau, this tau. So you see, if fourth condition is also satisfied by these n suffix x, what you're getting a topology where this collection n suffix x is precisely, the collection of neighborhoods of X. So this is a beautiful result. If you haven't understood it, like immediately read statement 3, 4, 5, 6 times, you will understood it. Trust me, when I have seen this first time, I was like, what's going on? But yeah, after a careful reading, I have understood it. So let me prove this. Proof. So what I want to tell you is, okay, let us prove it. So number one thing, phi belongs to tau vacuously. I have already told you this argument, right? We have discussed this in some lecture. So see, it is collection of, tau is collection of some subsets. If you take a point in that subset, but phi doesn't have that point, right? So vacuously, phi should be there. So it's a very beautiful logic in mathematics. Okay, so if you want to read more about this logic, refer metric spaces by, my god, sorry if I will do spelling mistakes. So Michael O. Sarkoid. I'm sure I have done a lot of spelling mistakes. I am very sorry for that. So Michael O. Sarkoid. The pronunciation is fine, so you can search about this text. Okay. Now, note that capital X belongs to tau. Why, guys? Let me do it. So what you have to check? For any point in X, right? So for X in X, choose say U in NX. Why we can choose this? Because I have told you these are non-empty collections. So if you have chosen that, what you have, guys? You have this thing. X is inside U, which is inside X. Now, by third property, you know what I am mentioning by 1, 2, 3. If you don't remember that property, stop the video, go back and see what is the property, or you may have written your notes. So by third property, so any member, if you have a member in this NX and that member is sitting inside some other member, then that member should be also in NX. So you see what you have got. So what you have got here, X belongs to NX for every X in X. So this implies X belongs to tau. So here what we have used third. Okay, good. And actually one also, because X is in U. So X is in U because we have 1. So that is again, you see, very important. Now let us proceed to the second thing. So let U comma V or V comma U where in tau. What we have to show? To show U intersection V is in where? Tau. Let us see why. So what you have to check again, for any point, the intersection should be in corresponding n suffix, that point. So for X in V intersection U, what you have, guys? This implies X is in V and what? X is in U. Where are VU? VU are in VU are in tau. So by definition, V should be in n suffix x. U should be also in n suffix x. Why? By definition of tau. Got it? Now, by second, since these nx satisfies second thing for every x, what you will have? Intersection is also there. So you see, intersection is there. So finally, what you have? V intersection U is in nx for every x in V intersection U. That's what you need to be something in tau. So this implies V intersection U is in tau. Let us do the third one. Or let me leave it for you. Please verify tau is closed under arbitrary unions. Okay, so hint, you may be using here, use 3. Okay, now, so what we have shown, so thus tau defined as all such u in x such that u belongs to nx for every x in u, right? If you have this condition, then u qualifies to be in tau, is a topology on x. Now let me do the final part. What we have to do? So assume nx also satisfies 4 for every x in x. What do you have to show? To show nx is collection of neighborhoods of the point x with respect to above topology tau. So let us see why this is happening. Okay, so I am gonna leave a few verifications for you guys. Okay, so let me begin it. So what you have to show, guys, that every member of nx is a neighborhood of x. So you assume let n belongs to n suffix x. What you have to show? To show n is neighborhood of small x, of course with respect to the above topology. Now to show that, you should produce an open set, right, containing a point in this containing x and which is sitting inside n. So let me have define something. So u to be what? Y in x such that n belongs to n suffix y. Now what is my claim? U contained in n, x belongs to u, and u is open in x with respect to the topology you have defined above. Okay, so I want to leave this as exercise. I'm leaving this as exercise. Please try it on your own. Spend some good amount of time. If you're frustrated, try it one time. Maybe try it for like after a week, but try it. Even then, if you have problem, you can always ask in comments of this video. So now, like I said, so we are done with this theorem. Sort of. Defining that open set was very tricky. So that is what I have done for you. So let us mention an application of this theorem. Okay. So let me have concluding remark or remarks. Above theorem is applied in something called fundamental theorem of infinite Galois theory. Okay? When you deal with something called profinite groups. See, this is a bit advanced topic. It uses also technique of the concept of direct and inverse limit, which is in commutative algebra, and this theorem, this way of constructing a topology. So this is very important, and whenever in your life you're gonna study this fundamental theorem of infinite Galois theory, you will recall this. I have done this thing. So just a thing I want to write here for profinite groups, because you see, like if you know about a little bit about Galois theory, so the correspondence which you see between subfields and subgroups, of course something called Galois group and the corresponding field associated with that Galois field. So that theorem in your first course you might have seen in finite dimensions. But in general, in infinite dimension, it is not true, that kind of correspondence. But it is true for something called profinite groups. So let me end this session by this remark. Thank you very much for your patience, and I hope this video is a bit knowledgeable for you guys. Thank you again.